Hi everyone, I am Dr. Lakshmi Viveka, Assistant Professor, Department of Chemistry in VNR VJEC. The subject it is Engineering Chemistry Laboratory. Today we have to learn about instrumental technique that is called as a colorimetric method. What is the colorimetric method? What is the importance of this colorimetric? Just you have to observe some images, some tomato ketchup, some fabrics with the color and dyes with the different colors and blood cells. So what is the common point in all these? So that is a colored substances. So here these colored substances consist of some amount of metals, and how much intensity of metals are present in that, and how can determine all these things by using this colorimetric method. So coming to the main objectives of this experiment, it is we have to measure the light absorption of solution at a specific wavelength, determination of concentration of substances using Beer-Lambert's law. It verifies the Beer-Lambert's law, and it can analyze the colored compounds in chemistry, biology and medical laboratories. You can compare the intensity of color between standard and unknown solutions. Coming to the applications of colorimetric technique, it is used in so many industries, mainly for the bioclinical estimation. We have to use this colorimeter. For bioclinical estimation, mainly it is used for the blood glucose levels for diabetic testing, and then protein estimation and how much amount of protein concentration in biochemical and clinical samples, and how much amount of hemoglobin is present in blood samples. Mainly it is used in hospitals and pathological labs. It is used to determine the impurities and how much amount of impurities and pollutants, some amount of metal ions which is present in the water, it can determine for water quality check. Then pharmaceutical analysis, mainly it is used in pharmaceutical industries for drug and chemical analysis. Now coming to the colorimetry technique, here we have to mainly focus on what is the light which is passed into the solution, what is the light and what is the source of light, and this source of light in electromagnetic spectrum, and what is the range, and this range it is in between 400 to 700 nanometers. And what is the instrument, what are the components of these instruments we have to learn today. Coming to the schematic diagram of this colorimetric technique and how it will be works, what is the working principle of this colorimetric technique, you should know about this one. So here, this source of light, what is the source of light we are using here? This is called as a monochromatic light. So the monochromatic light wavelength, it is in between 400 nanometers to 700 nanometers. Whenever light passes through a prism, so the monochromatic light, it diverges it in the form of VGR. So this VJR has different colors. Each color has its own wavelength. Here, whatever the solution we are taking into the cuvette, that based upon the solution color, we can choose the wavelength. That wavelength we can set up by using the filter disc. And here, based upon the how much amount of incident light is passed through the solution and how much amount of light is emitted, that is called as a transmitted light. Based upon that, we can take the absorbance values in the display. So that display values, it is in terms of optical densities. Optical density or absorbance values we can get on the display. So now coming to this main part, what are the components which are present in the colorimeter? What are the main components? Source of light, that source of light is a white light. The range of white light is a visible light. It is in between 400 to 700 nanometers. And the filter, it is a monochromator. It selects a specific wavelength. And the cuvette, we are using that cuvette which is placed in a cuvette holder. And this cuvette, it is used to hold the sample, that is either test solution or prepared solution. Then coming to the photo detector, this detector, it can detect the transmitted light. This detector, it detects the transmitted, how much amount of light is transmitted through this solution. This can be detected by using the photo detector. And coming to the finally, it is called as a display. This display shows the absorbance values based upon the concentration. So this is about the basic instrumentation of spectrophotometer. So coming to this experiment, the main aim of this experiment is we have to estimate amount of metal ions present in metallic solution. So that metallic solution, either we have to take copper sulfate or something ferrous sulfate, whatever it may be. So whatever the solution we are taking, that solution, it should be the complex form, it should be colored complex. So based upon the color, we can set the wavelength. Here metal ions, the copper ions, we have to estimate. These copper ions you have to estimate by using this given solution. That given solution, the test solution, it is called as a copper sulfate pentahydrated solution. So here, for doing this experiment, first we have to prepare a solution in different categories. So first, for calibration, we have to use a blank solution. That what is a blank solution, why we have to use that blank solution, we have to know. Then what is a standard solution, how many standard solutions we have to prepare, all this we have to know. And what is a test solution, based upon this concentration, how we can determine the estimated that is metal ions which is present in the metallic solution, we can determine using colorimetric technique. So here already I told you that is called as a copper sulfate solution. This copper sulfate solution we are taking, that is called as a stock solution. What is a stock solution? This stock solution, suppose I need to prepare 1 liter of solution. For this, we take 8 grams of copper sulfate. It dissolves in 1 liter of distilled water. Here, what is the concentration? Here, 1 liter, it consists of 8 grams. So 1 ml, it consists of 8 mg concentration. So whatever the solution we prepared, and that solution we have to use, that is called as a stock solution. That stock solution, first we have to place it in a beaker. So we have to charge it into beaker, and we have to add that solution, that is called as a ammonium hydroxide solution. The main ligand is ammonia ligand. This ammonium hydroxide, how you can prepare? Ammonia and water in equimolar ratio, we can get ammonium hydroxide. So this ammonium hydroxide we have to add to this copper sulfate solution. Then it forms as a complex. That complex, it is called as a tetraamino complex. So this complex, how it will mention? So here this is a central metal, that is called as copper, and it donates the ligands to this central metal. So these ligands are neutral, NH3, and it forms a outer sphere, that is SO4 minus 2. So the oxygen state of copper, it is +2. So we can mention it is as how many ligands are present and attached to the central metal? 4. So it is called as a tetraamino copper 2 sulfate. So this complex, it is formed in the form of blue colors. Initially it is a pale color, and finally after formation of complex, it forms as a dark blue color. So let us know how to prepare the standard solutions. For that, what are the apparatus and reagents are required for this experiment, you should know. So mainly stock solution we are using. That stock solution is called as a copper sulfate pentahydrated solution, and then complexing reagent we are using, that is called as a ammonium hydroxide solution, and distilled water we are used for making the standard solutions. Here we need standard flask or volumetric flask. 100 ml of volumetric flask, 8 flasks are required. Then cuvette, it is used for determination of absorbance of that particular solutions. Then we are using the major instrument, that is called as a colorimeter. Then burette, it is used to measure the solution which is filled in each standard flask. Then pipette, it is used for making the solution up to 100 ml. Up to the mark, we are used the pipette. So these are the apparatus and the reagents, and this is the setup for this technique. Now coming to the experimental procedure, just observe here. Here these are the different labeled standard flask. Each flask is labeled with a different volume. So it starts from 5 to and ends with a 35 ml. 5, 10, 15, 20, 25 ml, 30, 35 ml labeled volumetric flask we have to take in. Then what you have to do? First, we have to take the copper sulfate solution in that is 250 ml beaker, and we have to fill the burette with the copper sulfate solution in burette. So after filling the burette, just you have to, before filling the knob, it is closed. After filling, just you have to check the nozzle portion. Is there any air gap is present in the burette? Just you have to remove the air gap, fastly run on the solution and make up to 0 level. So then this burette you have to fix to the burette stand. Then just observe here. First, what you have to do? We have to fill the copper sulfate as per that volume in each standard flask, that is from 5 to 35 ml. Then to that, what you have to add? We have to add a complexing reagent that is called as a ammonium hydroxide. In each standard flask, we have to add 5 ml ammonium hydroxide. Just you have to observe here. In each standard flask, we have to add 5 ml of ammonium hydroxide. We have to measure by using the measuring cylinder and transfer it into copper sulfate solution. Then it turns to dark blue color. Then shake the solution. Then make up to 100 ml by using distilled water. So for that, we have to add distilled water up to the neck portion. So up to the neck portion we have to add, and the remaining portion use dropper up to the mark. Here this is a color solution. So color solution, the meniscus part, upper meniscus we have to consider. So in this way we have to prepare the solutions for different concentrations, that is from 5 to 35 mm. 5 ml to 35 ml. And also we will give you an unknown solution. That unknown solution concentration you don't know, you have to find out by plotting a graph between volume of copper sulfate on x-axis and the optical density values on y-axis. Further, to the unknown solution concentration we have to find out how much amount of copper is present in that unknown solution. So now coming to the determination of optical density, we have to use an instrument. That instrument is called as a colorimeter technique. So this colorimeter, it consists of different components. Just you have to observe the instrument, and it shows the display, and 61 it shows that is called as a wavelength. So here, this is the percentage of transmittance. The percentage of transmittance, and the same button we have to use it as auto 0. This is used for calibration purpose. Why we have to use this, why we have to do the calibration? Any instrument, before doing the experimentation, we have to calibrate for to get accurate results. To accuracy, we have to calibrate the instrument. For calibration, we are using a solution that is called as a blank solution. What is a blank solution? Why we are using blank solution? So blank solution means here what we have to do, we have to determine the intensity of the color, and based upon the wavelength we can determine the absorbance. So that solution, it has some metal ions. Here we are taking a solution, it has no color and no ions present in the solution. No color and no ions. So no color and no ions means it has a blank solution. So this blank solution, first we have to fill in cuvette. So that cuvette we have to place in a cuvette holder, and up to the 3/4 we have to fill in the cuvette. Then we have to follow the operating instructions here. First switch on the instrument, and then we have to select the appropriate mode of wavelength, that is 61. We can choose the wavelength either 58 or 61 or 65 based upon the solution color formed complexes. Based upon that we can choose the color, either we can increase or we can decrease the color. And here C1 and C2 are the mode of calibration. C1, C2 are the mode of calibration. When we press the C1 button, and we can, that means the light will blink at that particular, we need optical density values. So here first switch on the instrument and select the wavelength, then place the cuvette with the blank solution and place it is in the cuvette holder, then press the auto 0 button, that is absorbance 0, then automatically it comes to 0. Then what you have to do, we prepared already different concentrated solutions. Now replace the blank solution with the different solutions. We can find out the concentration for each solution. So you mainly focus on what is the calibration and why we have to do the calibration, what is the purpose of blank solution, and what is the blank solution we are using. That blank solution is called as a distilled water. Why we are using distilled water? Because it has no color and no ions. No color and no ions in the distilled water. That's why you have to choose distilled water as a blank solution. So the absorbance value for this distilled water is a 0. Then it is calibrated. And which filter number we are using? That is 60. In some instruments, in some other instruments it shows 61. That means it is multiplied with 10 nanometers. That is either 600 nanometers or 16 nanometers, right? So the wavelength we can choose. So why we have to choose that particular wavelength? Because the colored complex, it is a blue color solution. So the complementary color wavelength we have to set, that is in between 580 to 620 nanometers, or sometimes it is a 590 to 610 nanometers. So this range, the blue color complex wavelength, it is in between 580 to 620 nanometers range it is present. That's why you have to choose a 61 or 60 filter number. So here you mainly focus on what is the filter number, what is the importance of filter number, all these things. Filter number means already you know that colorimeter technique, it is an instrument to measure the concentration of the colored substances in solution by measuring the amount of light absorbed. It uses filters to select specific wavelength of light. So whatever the filter disc we are using, that filter disc, it is in the circular rotating plates. These circular rotating plates containing different colored optical filters. So here when just you have to observe here the blue color, then green, then orange or red color. So these are the complementary colors of the particular solution. So we can choose that filter based upon the color solutions. So what is the role of these filter discs? What filter disc helps in different ways? That is we can choose the wavelength, selective wavelength, then improving the accuracy and then absorbance of a measurement, then matching the complementary colors of the solution. Just to observe here, when look at this picture, a light which is passes through the prism, that light is a monochromatic light. This is the monochromatic light. Whenever it is enters to the prism, we can get different colors. Each color has its own wavelength. So already we discussed in the previous slides. So this is the light which is passed to the prism. We can get different wavelength. That light which is passed to the solution, so based upon that we can get the absorbance values. See here, whatever the light which is enters into this prism or solution, that light is a monochromatic light. It is under the visible light. This visible light, it is present in the electromagnetic spectrum. It is a small portion in the electromagnetic spectrum, that is in the range of 400 to 700 nanometers. And here some instruments, it shows a filter disc and filter numbers. Some instruments, it is in the form of percentage of transmittance, that is C1, C2 modes, then in the form of wavelength, that is 61 into 10, that is 610 nanometers. So the nanometers set we have to set. So I already told you why we have to choose that particular wavelength, 61 filter number. Why you have to choose? Because whatever the solution we are using, that solution is a blue color. So that blue color complementary color filter disc consists of either orange or red. It is in the range of this 600 nanometers. That's why we have to choose that particular wavelength. Now here, when monochromatic light passes through a colored solution, some specific wavelength of light are absorbed, which is related to the color intensity. The amount of light absorbed or it is transmitted by a colored solution, it is in the accordance with the two laws. So they are called as a Beer law and Lambert's law. So combiningly, these two are called as a Beer-Lambert's law. So this Beer-Lambert's law can be explained by this principle here. Whatever the light which is passes through a solution, here this solution, it is the colored solution. That complex we have to place in a cuvette. Here suppose 100% of light which is incident, that is I naught is called as a incident light. So 100% of light is incident through the solution. Some amount of light is absorbed and remaining light is emitted. 100 minus x is called as a emitted light. So IT is called as a emitted light or transmitted light. So here, how we can find out the percentage of transmittance? The percentage of transmittance, it is equal to emitted light divided by incident light I naught into 100. Okay, na? So percentage of transmittance is the IT divided by naught into 100. So what is the relation between the absorbance and transmittance? So these both are inversely proportional. Absorbance is inversely proportional to transmittance. Suppose we take a blank solution. So the blank solution is no color and no ions. So absorbance is 0. So transmitted light is 100% of light is passed through the blank solution. Then what happens? The same amount of light is emitted because it has no concentration. That's why it is emitted. So 100% of transmittance, absorbance 0, transmitted is 100%. So it is inversely proportional. When the absorbance increases, transmittance it is decreases. Okay. So the relation between the absorbance and transmittance, just you have to remember. Now coming to the Beer-Lambert's law. What is the Beer's law and what is the Lambert's law? So absorbance. So here we are using concentrations, different concentrations, that is 5 to 35 ml. When the color solution increases, that means the concentration of the solution increases, intensity of color also increases. Then we can get the absorbance values differently. So absorbance, it is directly proportional to the concentration of the solution and path length. The path length means it is the thickness of the absorbing medium. So simply we can say that A is equal to epsilon C into L. So epsilon is called as a proportionality constant. This is equation 1. And in terms of transmittance, we can mention it is as absorbance is a negative logarithm of transmittance. So negative logarithm of transmittance means here negative T means already you know that IT divided by I naught. So simply you can mention as equation 2. So combining these two, epsilon CL is equal to negative log of T. So finally the Beer-Lambert's law expression A is equal to epsilon CL equal to negative log of I by IT divided by I naught. So this is the Beer-Lambert's law expression. Here which one is the Beer's law? So Beer's law is the absorbance is directly proportional to the concentration is the Beer's law, and absorbance is directly proportional to the path length or thickness of the absorbing medium. The absorbing medium means either it is a quartz or glass or whatever the material we are used for making this cuvette. So the thickness of the absorbing medium, that is called as a path length. This is the Lambert's law. So by combining these two, we can say that so decreasing intensity of the light is directly proportional to the intensity, the concentration of the solution and then path length. Just you have to observe, already we prepared different solutions. When you take the absorbance values, so just you have to start from 5 ml. The value for 5 ml is a 0.11. It is missed here. And coming to the 10 ml, the value is 0.22. Observe here in the instrument. And 15 ml, it is a 0.33. For 20 ml, it is 0.44, 25 ml, 0.55. So it will be deviation is there for 30 ml, then 35 ml. So finally, we take the unknown solution. For unknown solution also, we have to prepare in same way like that. We take the, we will give you some solution. You have to add complexing reagent 5 ml, then make up to 100 ml by using distilled water. That we have to place in a cuvette holder. Cuvette that is placed in a cuvette holder, you can get the absorbance values. So now plot a graph between volume of copper sulfate on x-axis, the optical density values or absorbance values on y-axis. So here we can get a straight line, all the values you have to plot it on in this graph, then you can get a straight line that passes through origin. Here optical density suppose is a 0.29. So this 0.29 it cuts the straight line and it touches the x-axis. So that indicates that this is the, from these values we can get 13 ml is the unknown concentrated volume. So that 13 ml. So already we know that the stock solution concentration is a 8 mg. So that 8 mg we have to substitute here. That is amount of copper which is present in the unknown solution. That is the W1. W1 is a 13 into 8 mg. We can get 104 mg. Then amount of, what is the aim of our experiment? We can estimate the metal ions present in the metallic solution. So W2 we have to find out. That is how we can find out. W1 into molecular molecular weight of copper, that is 63.5 divided by molecular weight of copper sulfate pentahydrate 249.7. So we can get finally these values, 26.44 milligrams. So this is the final result of our experiment, the amount of copper present in the given sample solution. So that is a 26.44 milligrams. So here just take the error values, error how you can find out based upon the given values. So given values we can find out the error, percentage of error. Okay, right? So this is about the instrumental technique, colorimeter. So now finally go for the recap, what you understand from this experiment. What is the purpose of using colorimeter, and what is the complexing reagent we are using, what is the name of the complex formed, what is the blank solution, why we are using this blank solution, why don't you use other solutions, what is the calibration curve, and then source of light, which one we are using, and what is the filter we are using, and what is filter number, what are the different applications of colorimeter, all these things. Thank you. We will meet in the other video.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.